Hello, so we're now going to carry on with our Arenes work. I'm going to have a look at how the unusual structure of the benzene ring causes various different reactions to occur that we might not expect from our knowledge of alkenes. So we talked before about the delocalized pi cloud of electron density. And we also had a look at the alkene structure and the localized pi cloud there. And what we need to think about now is how that impacts the reactions that we're going to have. So when we talked about alkenes, we looked at electrophilic addition reactions. And we looked at how, as a molecule such as bromine approaches the carbon-carbon double bond, it will be polarized because the electrons are going to be repelled away from that electron-rich area of the carbon-carbon double bond. Now, we've said that benzene doesn't behave in the same way and that it won't decolorize bromine water. So we need to think about what it is about the benzene that means it's not able to react with that bromine molecule. So we can start off with our structures here. So when we have our pi cloud in our alkene here, we have got our 2 pi electrons spread over one carbon-carbon bond here. However, having a look at our benzene structure here, we've got our 6 pi electrons. So remember, we had 1 from each of the pz orbitals here that were delocalized. So we've got our 6 pi electrons spread over 6 carbon-carbon bonds. So this was 2 pi electrons spread over one carbon-carbon bond, 6 pi electrons spread over 6 carbon-carbon bonds. And so the electron density in this structure here is going to be much less. Now, if the electron density is less, then that means as the bromine molecule approaches, and if we remember, I'll draw it out for a normal carbon-carbon double bond like an alkene one there. As our bromine molecule approached, it would become polarized. So the electron density here repelled the electrons over this side of the molecule, shoving them over here. So this then became a little bit negative, leaving that a little bit positive. And then we had the mechanism that we're all familiar with now, where we have the electron pair here coming out and attacking that delta positive bromine, and then this one breaking and kicking off. We then went through, I might as well complete it just to do this properly. We then have opened up the carbon-carbon double bond. We've attached a bromine onto one end. This one must then be left with a positive charge. And then we've got a Br minus from the breaking of the bond. And so finally that came in and attached on. And then we had our 2 bromines attached across our carbon-carbon double bond. Now that was okay because we've got a region of high electron density here. But by looking at the ratio of the pi electrons here, so the 6 pi electrons over the 6 carbon-carbon bonds, we've got a lower electron density. So we find that the electron density is not sufficiently high to polarize the bromine molecule in order to be able to give it a strong enough charge in order to be able to attract to the electron density. So we only have reactions with the benzene if we bring along a catalyst, and we actually then need to create an electrophile that is going to have a full positive charge. So the partial positive charge was okay here because we've got a region of high electron density and it tracks it strongly enough. But with a region of lower electron density here, without a catalyst, the partial positive charge is too low and there isn't a strong enough attraction to cause a reaction there. So I'll talk about the reaction in general terms with an electrophile, and then we'll just have a little look at what's going to happen with halogenation, and we can use bromine as an example there. So in general terms, we start off with our benzene ring. What we need is an electrophile, and I'm just going to call it E+, but it will have that full positive charge there. Now, we have got a region of high electron density, it's just not high enough in order to polarize the bromine molecule sufficiently, and it always needs a catalyst to react. And so we are going to have electrons from here, so a pair of electrons donated by a curly arrow, coming out and attacking our electrophile like that. Now, it's very important that your curly arrow starts just on the ring and goes to E plus there. Okay, so we don't want to see it coming from in the middle of the ring, because the ring's supposed to denote those pi electrons, so it needs to come from there. Now, once that has happened, we now have formed a bond between a carbon atom and our electrophile, and we've involved two of our pi electrons, which means that we no longer have a full ring because two of them have gone to bond with our electrophile. So we could draw on our bonded electrophile. Remember that each of the carbons has a hydrogen, so we're going to draw that hydrogen on, so the one that's on the same carbon with our electrophile. And we now have a partial ring. So we draw, it opens up, and it always faces the carbon that's now got the electrophile on, because this side, all the PZs are still overlapping and delocalized, but here our pair of electrons has gone to bond over here. And this is going to have a positive charge. And we can check through, that had a positive charge, so this needs a positive charge. Now, that is going to be really unstable. We need to reform our ring. So in reforming our ring, we're going to lose our hydrogen. So from midway along the carbon-hydrogen bond here, the electron pair there is going to go back into the ring. And so the end of our reaction is going to be the ring reformed. We've got our electrophile now nicely attached, and we've kicked off an H+. So that's a generalized structure. Okay, so that's kind of showing a generalized reaction with a random electrophile E+, but you need to know about specific electrophiles, and you go through these in turn in the notes. I'm going to talk you through, first of all, we'll stick with bromine just for sake of argument, and then you can have a look at individual ones through the PowerPoint and the theory. So we said we need to generate this electrophile, so we can't just use a bromine molecule. And what we do is we use something called a halogen carrier. Now, a halogen carrier is typically the aluminium halide or the iron halide. So if we're going to react with bromine, we're going to use the aluminium bromides there. And we're going to react that with Br2. Okay, now if you remember, aluminium has 3 electrons in its outer shell, and that means that our Br3 here, aluminium's unusual and can do kind of covalent bonding because it's tiny size there. So we've got 3 of the bromines attached, and we've got then 6 electrons around our outer shell of aluminium, 3 of its own, 3 overlapping with the bromine. It means it's got space to accept 2 more electrons, and it does that by accepting one of the bromines. So what we form is AlBr4- and our Br+ electrophile. Now we're completely used to bromide ions being Br-, so this is an unusual situation, and this is our electrophile. Now once we've got our electrophile, we're away. We just do what we've got up there. So we start off with our benzene ring. We have our Br+ electrophile. We have our curly arrow start at the ring and come out to our Br+. And that means then that the ring is broken. We add on our bromine and we draw on the hydrogen that was there in the first place. Our ring is opened up in the direction of the carbon that's now got the bromine, and we put the positive charge. And then, this is our intermediate, then we're going to break the carbon-hydrogen bond, and the electrons from that are going to come back and reform the ring. Okay, so we can draw that out. Oops, slightly wonky there. Let me move you along slightly. So we can draw that out, we reform the ring, and we've got our bromine and our H+. Now I said earlier that we need a catalyst. So we wanted to react with bromine, We brought in our aluminium bromide, and that is the catalyst. So what we now need to do is show that it's behaved as a catalyst. So in our generation of our electrophile up here, we formed AlBr4-, and what we can now do is bring that in and we can allow the catalyst to be regenerated. So our AlBr4- here can react with the H+ ion formed during our mechanism stage there, and that would give us AlBr3, so we've got a catalyst regenerated, plus HBr. So overall, our overall reaction looks like this. So overall we have our benzene ring, the aluminium bromide we've just said was the catalyst. So our benzene ring will react with bromine, forming our bromobenzene. We should be happy naming that after learning that last time. And remember, the H got kicked off here. Take the other bromine to give us our HBr. Now, in terms of a name of the mechanism for this, we've used an electrophile. So we had our Br+ as an electrophile. But if we have a look at what actually went on during the reaction, our hydrogen that was attached to our carbon here has been replaced by the bromine. So this is going to be electrophilic substitution. So we've got an electrophile there, so an electron pair acceptor, which is done here. And we've got a substitution reaction, which is where one atomal group is replaced by another atomal group. So our hydrogen was replaced by our bromine. So now you need to continue on through the PowerPoint, looking at the different examples and the different catalysts as we go through. And then once you've done that, have a practice at drawing out some mechanisms for yourself, and then working out and suggesting what an electrophile might need to look like in order to produce particular products.